Okay, I'm going to go ahead and begin section 5.6 now, which is solving exponential and logarithmic equations. We did a little bit with exponential equations in section 5.3, and we'll do some more of that here now. Actually, I'm going to start with some logarithmic equations, and the best thing to do here is just to show you guys several examples of where we're solving equations. So when it comes to logarithms, when you're solving a logarithmic equation, typically you're going to be using the definition of a logarithm and or properties of logarithms during the process of solving. Remember, the definition of a logarithm is y equal log base a of x, means that x equals a to the y. Okay, so in this first example, I want to solve for x. And let's get rid of the logarithmic notation by rewriting this into exponential form using the definition. 7 minus 4x is my input, so that's going to be all alone on the one side of the exponential. 3 is the base, 2 is the y value, and so 3 squared would be on the other side. And now I'm back on familiar ground because I no longer have the logarithmic notation going on. So also 3 squared is 9. And if you subtract 7 and then divide by negative 4, we get x equal negative 1/2. Now, one of the things that you'll want to do when you're solving a logarithmic equation is you'll want to check your answers, because we can sometimes have extraneous solutions. If I were to plug negative 1/2 into the original equation, negative 4 times negative 1/2 is 2, 7 plus 2 is 9, and so log base 3 of 9, log base 3 of 9, that'd be the same as log base 3 of 3 squared, and I know powers can come out of logarithms, right? And that's law 3, and that list of laws that I gave you. Log base 3 of 3 is 1, that's law 5 on that list of logarithms that I gave you, and so I'm looking at 2 times 1 is 2. Okay, 2 is also the number that I see on the other side of the equation. 2 equal 2, that's a true statement. So x equal negative 1/2 would be the answer there. Okay, here's another one. Same deal, solve for x. So with this guy here, let's get the logarithms on the same side. I've got the same base, so I can combine these to a single logarithm by multiplying the inner terms. 4x times x is 4x squared. And then I'd say at this point, why don't we lose the logarithmic notation? We'll convert this to an exponential. 4x squared is my input, so that's going to be all alone on the exponential. 2 is the base. 2 here is the y value, so 2 squared would go on the other side. 2 squared is 4, and if you divide by 4 and take the square root of both sides, we get x equal plus or minus 1. Negative 1 would be extraneous because we can't take log of a negative. So throw that one away. If x is 1, then we've got log base 2 of 4. Actually, if I use this line here, log base 2 of 4 plus log base 2 of 1. Well, log base anything of 1 is 0. And so is log base 2 of 4 equal to 2? Yeah, because log base 2 of 4 is the same as 2 squared, and I can bring that 2 in front. Log base 2 of 2 is 1. 2 times 1 is 2, and that's the number that I see on the other side of the equation here. So 1 is going to be kept, negative 1 is extraneous. Here's another equation. We're solving for x. 2 is a multiplier. You'd want to bring that inside the logarithm so that it's the power of the inner part. That way you don't have any multipliers in front of the logarithmic notation. Since you have a logarithm on both sides of this equation, you can remove the logarithmic notation and set the inner terms to be equal. So that's what I've done on the next line. And then FOIL out x minus 1 times x minus 1 and get everything onto one side so that we now have a quadratic. X squared minus 3x, x is in common to those two terms. When you factor out x and set the factors equal to 0, you get x equals 0 or x equal 3. 0 would be extraneous because when you plug that into the original, you have log of a negative, which cannot be calculated, so throw that number away. If you plug in 3, you'll have ln of 4. And then 2 times the ln of 2, well, the 2 can be brought up. 2 squared is 4, so you'll have ln 4 on the other side. ln 4 equal ln 4, that's true. So 3 is going to be kept there. The next example, okay, we want to again solve for x. With this one, you can combine the 2 logarithms to a single logarithm by multiplying the inner terms. And then I'd say at this point here, why don't we use the definition of a logarithm to get rid of the logarithmic notation. Actually, another way to go about it is, so 1 is the same as log base 4 of 4. And if you get a little creative with that, you know, we now have log base 4 on both sides, and so you can remove the log base 4 notation, and you'll have x squared minus 3x equal 4. Subtract 4 from both sides, so x squared minus 3x minus 4 equals 0. That equation will factor nicely, and we end up getting x equal negative 1 and x equal 4. Negative 1 is extraneous since you can't take log of a negative. 4 will be kept though. If you plug that into the original, log base 4 of 4 is 1. Log base 4 of 1 is 0. 1 plus 0 is 1. That's true. Now, at this point, I had mentioned that you could have used the definition of a logarithm also. You would have still gotten to the same point here in the calculation, you know, if that definition was applied correctly there. Okay, here's another example. We're solving for x. I'm subtracting logarithms, and so I'm going to combine those to a single logarithm by dividing the inner terms. I've got base 10. So when I apply the definition for removing the logarithmic notation, 11x plus 9 over x plus 3, that's my input, so that's going to be all alone on the exponential. 10 is the base, 3 is the y value, so 10 cubed would be on the other side. 10 cubed is 1,000. And if we multiply both sides by x plus 3, and then distribute 1,000, then that's how I'm getting this next line here. If you subtract 11x and then subtract 3,000, and then divide by 989, then we've got x equal negative 2,991 over 989. In decimal form, that would be roughly about negative 3.02, and that's probably how I'd want to look at that number because I want to check that number. Negative 3.02 plus 3 is negative 0.02, and I can't take log of a negative, so that number would be extraneous. There are no solutions. That was the one and only number. It didn't work out. No solutions to that one. This next example that I had, I'm going to actually skip. This was just kind of a neat problem that I was going to use to maybe kill some time, but it wouldn't be anything that I would ask on a quiz or a test. But you can look at how that was done if you want. We're going to move on to exponential equations. Now we've already done a little bit with exponential equations here. The plan in section 5.3 was to get the same base on both sides. So like if I want to solve this equation here, 2 to the x equal 8, 2 cubed is the same as 8, and I can get base 2 then on both sides, remove the 2's and set the powers to be equal. X equal 3 would be correct. Now with an exponential, you don't need to bother checking your answer. Okay, we only need to do that with a logarithmic equation for problems in this section. So a problem like this isn't so bad, right? Because we were able to very easily get the same base on both sides. Now in this next example, if I got 2 to the x equals 7 and I want to solve for x, the problem becomes more difficult because 7 is not a power of 2 like 8 was. In this situation where you can't get the same base on both sides, you want to get logarithms involved in the calculation. Usually we use the natural logarithm. I'll comment on that on the next problem. But really you can use any base if you want. So if I take the ln of both sides, that allows me to bring the power in front of the logarithm on the left using law 3. And ln2 is just a number, right? So divide by that number, And so ln7 over ln2, that'd be the exact answer for x, or roughly 2.81 would be the approximation in decimal form there if you round to 2 digits. Typically, we take the natural logarithm or base 10 in the calculation. If we need to go to the calculator, that would be preferred. You don't need to take base e or base 10. Like in this problem, I could have taken log base 2 of both sides. If I were to do that, x comes out in front just as before. Log base 2 of 2 is 1, and so that leaves you with x times 1 is x. Log base 2 of 7, that would be the exact answer. Okay, but if we wanted to know what that is in a decimal form, we would need to use the change of base formula. And remember that when we use the change of base formula, we prefer to change the base to either base e or base 10 so that we can go to the calculator and use either the ln button or the log button. So to me, it makes the most sense to just use base e or base 10 to start. Otherwise, you got to change the base at the very end, which, you know, why do that if you could just start with that base e or base 10? Okay. Here's another equation. So we will again need to do something with logarithms since we're not going to be able to get the same base on both sides here. If I take the ln of both sides, that allows the powers to come in front of the logarithms. Now, one reason for taking the natural logarithm is because many times we work with base e. Base e is the most common base for exponentials, and the ln of e is 1. So on the left, I'll have just 2x times 1 is 2x. On the right, distribute ln 5, and I'm going to subtract x ln 5 from both sides and factor out x on the left from those two terms. 2 minus ln 5 is just a number, like 5 is a number, so I'd want to divide by that number so that x is all alone now. Negative 3 ln 5 over 2 minus ln 5, that would be the exact answer. In decimal form, if you go nearest 2 digits, you get roughly negative 12.36. Pay attention to how the answer should be on MyMathLab if they want the exact form or if they want some decimal form rounded to, you know, a certain spot where they would tell you in the problem. Okay. Here's another example. So again, I'm going to have to change the, or I'm going to have to get logarithms into the calculation since I'm not going to be able to get the same base on both sides there. So if I start by taking the ln of both sides, that allows the powers to come in front of the logarithms. And I would also add that you'd want to make sure that you've got parentheses around that those expressions representing the powers, since you'll want to distribute ln 6 and ln 4 on the next line. And so that's what I've done here on the next line, distributed. Anything involving x, I'm going to get that on the left. All the other numbers, I'm going to get that on the right. X would be in common to these two terms on the left, so I have factored that out. ln 6 minus 2 ln 4 is just a number, so I would divide both sides by that number. That way x is all alone. Negative ln 4 minus ln 6 all over ln 6 minus 2 ln 4 would be roughly 3.24 in decimal form. If you type in the whole thing all at once, you'd want parentheses around the numerator and also the denominator, just so your calculator knows to divide at the very end. Okay, that would be likely the problem if you were not getting this decimal, if you were trying that on your own there. Okay. Here's another kind of similar example. You can look at that on your own. So again, the bases are not going to match up. You're going to take the ln of both sides. The power comes out in front, and you're going to distribute and continue solving for x there. This problem to me is very similar to the last one. I've got one more here. So in this problem, 4 to the x, well, 4 is the same as 2 squared, and 2 squared to the x, that's the same as 2x squared, 2 to the x squared, because by my rules of exponents, I'm just going to be multiplying the powers there. Now the reason why I've written it like this, and also 2 to the power x plus 1, that's the same as 2 to the x times 2 to the first, using law 1 on that list of laws of exponents. And now the idea here is that we want to recognize this as an exponential equation, but it's also a quadratic, right? I've got a squared term, a linear term, a constant. I'm adding all three of those together to get 0 on the right. That's what we do with a quadratic. And I'm going to let u be 2 to the x. If I square both sides in this equation here, u squared would be 2 to the x squared, and that's what I have leading off there. Replace that with a u squared. Minus 2 times 2 to the x, well, 2 to the x is u, so it'll be a minus 2u minus 8, that's all equal to 0. And at this point I can see more clear now that I actually had a quadratic. Okay, it was a quadratic all along, it's just kind of hidden in disguise a little bit. But knowing that I've got a quadratic means that the next thing I want to do is factor. Here would be the factored form, and when you set the factors equal to 0 and solve, you get u equal 4 or u equal negative 2. Now, we don't care what u is, we care what x is, right? We're solving this original equation here for x, and so I would say at this point, substitute back, u is 2 to the x, and so you'll have 2 to the x equal 4 or 2 to the x equal negative 2. Now, 2 to the x will never be a negative, no matter what x is. So I've got this crossed out here because there's going to be no solutions to this equation. I know 2 squared is 4, so x would be 2, and 2 therefore would be the solution to this equation. I think there's like 1 or 2 problems where you're solving an exponential, but it's also a quadratic in this section. So here'd be a similar problem. Okay, here's the homework problems in section 5.6. We're now done with section 5.6.